Hello, can everyone hear me? Uh, Afzal, can you hear me? Just want to confirm. And if you're able to hear me, do let me know. I'll also start to share my screen. Um, let's see if that is possible. Give me just 1 second. Right. Yes, perfect. So let me start by sharing my screen. Uh, Good. All right. So I hope everyone is able to also see my screen. Can you just confirm? Um, Afzal, if you can just confirm if you're able to also see my screen. Because it's been quite a while since I've shared my screen on Discord. So just wanted to ensure if you're able to hear me and see my screen. All right, perfect. So again, welcome everyone to the next session of the TensorFlow user group Durg StudyJam. We have been having a set of different functions or different classes on machine learning. We started off with an introduction to what AI is, some of the mathematics behind AI, and then gradually we moved over to talking about the regression algorithm. Now, before we jump into what the KNN algorithm means, we'll just have a quick recap of the supervised set of algorithms, right? So, in a basic supervised learning algorithm, ultimately what we are going to be having is that you have a bunch of raw data, and based on this raw data, you would basically also have the label associated with each and every data, right? For example, if you have a set of images, so let's say that you have all these images with you. It could be an image of a cat, or it could be an image of a dog. Let's say that you are trying to classify whether an image contains image of a cat or a dog. So your training data will actually contain the label associated with your data. So every single data that actually is now being sent to the machine learning algorithm, uh, that is part of the supervised learning algorithm, will also have the label. And based on this, we'll be able to have these set of predetermined classes. So once you send this to your ML algorithm, right, it will already know that it has to create an n set of, or a preset of, or actually the word would be a preset of classes, right? Based on the labels of the data that you are basically sharing with your dataset. In this case, there will be a class containing images of cats, and there will be a separate class containing images of dogs. So in case of a supervised learning algorithm, the amount of effort required by the AI algorithm, or in this case, the machine learning algorithm, basically reduces quite considerably, because now you don't have to create automated clusters that actually take place inside of unsupervised learning. In supervised learning, you're already providing that data which is required for you to calculate, okay, whether the data set has like the labels or not. So in this case, we are already providing the labels and we have these predetermined classes. And we don't have to like create automated clusters, right? We already have these trained classes. And now whenever you are getting a new data set that needs to be predicted, it will exist out of those n set of predetermined clusters or predetermined classes. So if you're giving it a new image, it'll of course use machine learning algorithm to find the closest set of features that match with this new data that you have just given to the algorithm, and you'll be able to make a prediction that okay, whatever class or the set of values from a particular class are the closest in terms of the features, those will be the ones that will be made the prediction, and we'll be able to get the output. That's a quick gist into what the supervised learning algorithms is. Now, within supervised learning, you have primarily two different type of tasks that you can do. So you have classification and you have regression. Now, regression was already covered in the last section. We'll focus instead more on classification. Now, one of the key differences between classification and regression is the type of data that we actually deal with. Whereas with regression type of algorithms, you're mostly dealing with continuous data. That means data that is recorded over time, and any two particular data points are actually in some way interrelated to each other. For example, if you are capturing amount of rainfall that took place an entire year in, let's say, Durg, right? So you calculate the amount of rainfall every minute, or the humidity that's taking place every minute. So when you calculate the percentage of humidity at 4 p.m. and at 4:01, so the humidity at 4:01 is dependent on the humidity that's taking place at 4. So whenever you're dealing with regression style of algorithms, you're typically dealing with continuous data, whereas with your classification algorithms, you're primarily dealing with just distinct data, right? And I think like the other word we can say is, instead of using continuous data, you're using discrete data. So if we say that okay, we are using images of these cats and dogs, we can confidently say that an image of a random cat and an image of a random dog are not interlinked with each other. In fact, like even two images of cats are separate entities. They're not related to each other in any way. Like all of them are individual images, right? So one image does not actually have any sort of impact on another image. So while dealing with classification-based algorithms, we're dealing with discrete data, right? Now, since we're focusing on the classification style of algorithms, let's also just go a bit understanding that how classification set of algorithms actually work. So you will basically first start with the task of categorizing your input into the discrete classes. For example, here we have given an example of an input image where the output could be probabilities of image containing images of dogs, cat, horse, and zebras. That means that every image will have a label associated with it that will either belong to dog, cat, horse, or zebra. And since it's a supervised task, we already know the labels for each and every input. So here, once we go through the input training process, we will create these classes, these four different classes. And once the training process has been done, when it now comes to actually classify a document into the predefined categories, which these can be dogs, cats, horse, or zebras. So then, the information can actually be in images or it can be in text. It does not really matter, because in either way, you would go through a transformation of converting either the text or the image into a mathematical vector, right? You'll find okay, based on the new data that you've given, using a certain algorithm, which particular uh, class is actually the values from a class are the nearest to the data that you're trying to classify, and that will help you to calculate the overall value. That's in a nutshell what the classification set of uh, category of algorithms basically mean. This brings us to the first official algorithm that we are going to be covering today, which is known as the KNN classification algorithm. So we call it as the K nearest neighbors algorithm. So this is a supervised learning algorithm. It is a classification based algorithm, and we'll now just understand that how it actually works behind the scenes. So here the word K, if you're hearing this term for the first time, of course it might be a bit confusing to you that what is this K? So we'll jump into that aspect a bit later, um, when we basically lay down the steps of the algorithm or how the algorithm basically works. But before that, we will do a basic mathematical exercise because, of course, with every algorithm, there is certain set of mathematical functions that are used. So in the case of the KNN algorithm, the mathematical concept that we learned today is known as the Euclidean distance. There are different type of distances also used for KNN algorithm. There is Manhattan distance, but today we'll focus on the Euclidean distance formula, right? We'll not talk about the Manhattan distance, but that's something that you can study on your own. Or if you have any questions, drop them in the Discord channel. We will focus today. This will be our focus. So focus on this today, which is the Euclidean distance. Now, in a very simple layman terms, basically the Euclidean distance is nothing but it's basically when you are having any 2 points on your Cartesian plane. So you could have the points A and you have the point B, and the coordinates over here, which are mentioned as y1, x1, and then x2 and y2. So basically, you want to calculate the distance between these two, right? The distance between these two. So the way that you would basically calculate this distance would be the square root of, so the distance would actually be the square root of x2 minus x1 whole squared, right? Plus y2 minus y1 whole squared. So you're basically calculating the total distance of the hypotenuse, because you can think of this as a right angled triangle. So you're calculating the distance between points A and B. That's the square root of the difference of the individual coordinates on x and y and squaring that and adding them together. So this gives you the Euclidean distance. Now, if you just think logically that in case there are there are 2 points, so let's take this as an example. So we have point A, we have point C, and this is point B. So of course, you can calculate two different distances. One is A and B, and you have the distance A and C. So of course, it is clear that distance AB is less than distance AC, right? Now, what does this actually mean in real life? Because we know that these points are essentially representing the real world features of any data, right? So when there are 2 points which are closer to each other, we can very confidently say that their features match closer in real world. So if the Euclidean distance between any 2 points is smaller, that means that their real life features match closely. And when the 2 points are further away, then their real world features also do not match that much. So that is why if you just think about the full form of the KNN algorithm, which basically means K nearest neighbors, we are trying to find the nearest neighbors to a given point, because that allows us to help to find the class or the set of values that belong to a particular class, which are matching features closest to the given point that we wish to classify. And that will be the predicted output that, okay, this particular new point belongs to so and so class because the features that are there in this particular class are closest to set of features. Type of data that you're basically dealing with is that, okay, let's say that you have an example of 3 different classes. So you have a set of values that are like this, right? So this is one class that you have, which can be class A. Then you have this another class, which can be thought of as class B, and you have another class. So this can be thought of as class C. You have these 3 different classes, and then let's say that this is the point that you wish to classify because you don't know. So essentially, all of them are kind of occupying their own kind of segments within this entire Cartesian plane, and there might be some overlapping here and there. So there might be some parts of the C algorithm that or of the C class that have some of the points that are intersecting with each other, but basically this should give you an idea that how how all of them kind of occupy certain parts of the Cartesian plane, because of course all of those points are similar in their in nature and in their physical properties, in their features, right? So that is a basic gist of how that kind of functions. And now we'll understand that how we can actually apply the steps of the KNN algorithms. We'll go step by step into understanding how KNN algorithm works, and then we'll jump into doing the actual Python implementation for the KNN algorithm alongside a project that we'll build for the KNN algorithm. So now let's start with the steps. So I'll go a bit, let me zoom in a bit more. So we'll start with the steps of the KNN algorithm. So the first step is to define a value of K. Now, again, I mentioned earlier that we will describe what is the significance of K over here. So K is this random value, or just a predefined value that you select. And the goal of this value is to define how many number of closest values that are closest to the point that you wish to classify Euclidean distance wise. So you calculate the Euclidean distance of the point that you wish to classify from all the other points that are already there in our data set. And so you that are the closest to the given point. Let's say n number of the closest points. And then it serves the purpose for us to actually make the prediction that what is going to be the outcome. So for now, let's say that we define a value of K, and we can select any random value of K. We'll learn later that how do you actually, what should be the most optimized value of K that you should pick. Because of course, I mean, when I say that pick a value, I could pick a value of K as 1. I could pick a value of K as 500. I could pick up the value of K as 1000. But there are certain values which might be the best for the given function or for the given particular project that you're trying to build, because the data set for every project will vary based on the project. So let's just select a value of K. For now, let's say that we'll pick the value of K as 5, just as an example, right? Then what you do is, of course, in the case of the KNN algorithm, you have, let's say, a point A. So A is a point that needs to be classified using KNN. So what you go ahead and do is, and let's just draw a diagram as well. I mean, I think just to make this a bit better understanding. So here was, class A with all these points. Here was class B with all these points, and class C all these points. And let's say that you want to classify this point A. So actually, I can call it like X point X. So here, X. So basically, X is a point that needs to be classified using the KNN algorithm. So the next step for you would be that you basically calculate the Euclidean distance of point X with all the points in our training dataset. So let's say that our training dataset is going to be a list. So it'll be a list of values. So we have the training. So we can say that since it's a list, so we'll run a loop. We will calculate the Euclidean distance of the point that we wish to classify with all the points that exist inside of the list, right? Of the list of values that are already trained. So what you end up getting is basically this distance list, right? Which is basically containing D1, distance D1, distance D2, all the way till distance Dn. So thinking or considering that we have n number of points in our dataset, so we have n number of points in the dataset, right? So this is what we end up with. So you calculate the Euclidean distance of the point that you wish to classify against all the different points that are already existing in our data. The next step after this would be that you go ahead and you sort them in an ascending order. So you sort all of these distances in an ascending order. So let's say that you have a list be equal to di is less than, or you can say d1i, d1 is less than, just want to make it a different notation. So di1 is less than di2 is less than di3 is less than, so forward till din. So we get our sorted distance list. So this is now in ascending order. That means whatever distance was the smallest, that would mean that that particular point is closest to the point that we wish to classify. Here is the basically the next step where we pick up the value of k. So here we will use the value of k over here. And the way that we're going to be using it, that think of using k to find a subset of the current distance list, of the sorted distance list, to find the k shortest values. So basically, if you say, okay, I have my n number of distances are 100. I have 100 distance list array. Now you have sorted it. So it's a 100 sorted array list. Then what you do is you pick the value of k as 5. So basically, that would mean that I'll create a sub array or a sub list, which will have the five shortest distances, right? So you'd end up taking the value of k. So you are left with the, so we can say the k shortest distances, which will be an array, which basically consists of d1i is smaller than di2 is smaller till you reach the value of dik, right? So basically that is the entire idea. Now, so basically you're left with k smallest distances. That means the for example, if k value is 5, that means the 5 smallest distances, or the 5 points that are closest to the point that you wish to classify. So let's say that since we took an example of k as equal to 5, so we took the value of k as, or k as equal to 5 in this example. So the 1i, of course, is the distance between the point x that we wish to classify from one of the points. So let's say now, since we already know that what that particular point actually represents, right? We already know that since we're calculating the Euclidean distance of the point from, like, let's say a point I, we already know what the point I, which class does it actually belong to, because these are all the pre-trained data, right? So based on this, let's say that di1 was the data that was from A, then I2 would be x from a point that belongs to class B, let's say, and then I3 is belonging to is from the class A again. di4 is basically again from class A. I'm just like giving an example. And di5 is, let's say, from a class from C. So we now have this information, right? We have this information of which particular class does that particular point belong to. And then we calculate the 5 smallest distances. Now, this is where the final step of the algorithm comes into the picture. Now, a lot of you might have actually studied the mode of any data. So calculating mode. So it is a statistical function that returns, statistical function that basically returns the highest occurring value. So in this case, if I were to calculate the mode of this entire data, what would be the result? It would be A, because A is the most occurring value. And this is what the prediction is going to be. So the prediction being made by the algorithm is that, okay, given the fact that the most amount of data points belong, or the maximum amount of data points belong to the class A, that is, I'm going to now make the prediction that even the point X belongs to class A. So it works on the majority rule. Of course, there could be situations where, let's say that we would have had a situation where di4 would not have actually belonged to A, but probably might have been belonged to B. Then the mode of the data would not have given you one result. So in that case, you might have to tweak the value of k, or perhaps do something else in order to ensure that you don't end up in this kind of a situation. Similarly, like for example, if you have, let's say, just two classes, so ideally you should not pick the value of k as 2 ever, right? Because it might be a situation where d1i is belongs to class A, and d1 I2 belongs to class B. So it's again a tie. We don't want that to happen. But I hope that that kind of gives you the sense of what the steps of the algorithm are, right? You start with the value of k, which basically defines how many closest set of values you actually want to look at. Then you calculate what is the distance list. You calculate the Euclidean distance, you sort it, you find the sublist of the smallest distances, then you calculate the mode of the data, that means what is the most occurring value, and that's the result that you are basically expecting. So that is in a nutshell what the theory of the KNN algorithm kind of looks like. We'll also dive deeper into understanding like how does one actually go about trying to find the most optimized value of k, because of course, as you might see, right, that the k basically the k really forms a really important aspect while determining what how many number of neighbors do you actually want to choose. Because there can be a situation where, of course, in this example, we took the value of k as 5. But if you would have chosen the value of k as 7, let's say that the distance 6 would have been from point B, and distance 7 would also have been from point B, then the result would actually change, right? So it's not that given a fixed value of k or any value of k, the result will always be the same. You might change the value of k and you might get different results. The overall idea is that based on the results that you're getting, are those accurate? Because ultimately, like the AI algorithm or the machine learning algorithm can give you any result, but only there'll be certain results that will be accurate, which will make sense. In this case, we will understand that a bit later. That how do you actually identify what is the ideal value of k? What is the value of k that you want to basically use, right? And of course, it will also depend on what kind of distance algorithm do you actually use. So we covered the Euclidean distance. We also have the Manhattan distance. We have the Minkowski distance, and we have the Hamming distance. So there are different types of values of k. Now, when you want to select an optimal value of k, you can define a range of the k value. So like let's say anywhere from 1 to 20. And then you can always basically choose a metric through which you want to identify how is your algorithm basically performing. So you'll define a performance metric for the algorithm, like calculating the accuracy, the recall value, the precision value, and using that to actually identify what will be the most ideal value of k. But we'll select like a very simple way to understand using trying to identify, okay, the amount of error that is there, like the mean squared error, as an example, to find, okay, what is the most optimal value of k for a given data set. So we'll also do that in today's exercise. So I think that kind of sums up what I wanted to quickly cover in terms of the theory. I'll come back to the Excalidraw in a bit, but let's open my Collab notebook now and implement the KNN algorithm. So I will go ahead and create a new notebook, and we will quickly just go ahead and sync it over here. So let's go ahead and connect it. So we'll start to implement the actual KNN algorithm now. And again, if anyone has any questions, do share your questions that you might have, right? I would love to answer those particular questions. So let's start the implementation of the algorithm, right? Uh, and again, at any point in time, if you have any questions, do share those across. So we'll import, our of course our important libraries first. So we'll just import NumPy as NP, import pandas as PD, right? And now we will go ahead and implement the actual KNN algorithm. So first, let's define a particular class for our algorithm. So in this case, what we are going to be doing is that, of course, there are a few important aspects of what the algorithm, how the algorithm is going to be actually creating. So we are going to be having a function for calculating the Euclidean distance. We are going to be having a function that will first also then calculate the mode of the data, right? Because you want to calculate what is the most occurring value, right? What is the most occurring value? So let's first define, let's start by defining or constructing a KNN class. So let's have a separate class over here. So we'll define this class as, let's say, K neighbors classifier class. And in this, what we're going to be doing is that we'll have our init function. So we'll define our different methods. So we'll first define our init method, which we can just define k over here, and then we can pass on another additional value. So it could be like what is actually the distance metric that you want to define. So in this case, you could have the distance metric as being Euclidean, because of course, as I mentioned, that there can be different type of methods that you can use. And here we'll just do this, and we'll also have self dot dist metric, right? So let's just define this, which will be equal to Euclidean. So this is going to be our function that we are going to be defining. And sorry, my bad. So this will be dist metric. Okay, perfect. So now, once you have defined this particular value over here, let's also define the function that will help us to fit our values. So the fit will be used for basically training the algorithm. So here, instead of x train, we'll pass x train and y train, because we are training it over this particular data. So we'll just replace these values over here. Similarly, y train. We'll just define our training class over here. So this is our init class and our fit class. So the idea is that now the bulk of the KNN algorithm will be performed by the predict function, where we'll have a data set of attributes that will be iterated upon point by point, for which we'll find the distance, which is the Euclidean distance. We will now use that training data classes will be sorted in a list in ascending order. Then the first K classes will be kept and stored in a separate list, which will simply just map to the nearest neighbors using the most common function, which will return a set of predictions that will be for every single point that we wish to classify inside of our data. So let's go ahead and define our predict function over here. We'll have def predict, and this will basically pass our self and our x test, which is basically a list of values that need to be classified. Now, initially, let's define an empty list, which is called as neighbors. And now we'll basically just do for x in x test, right? And then we'll simply write the logic. Let's say that we define distances is equal to. So basically here we are going to be using we are basically going to calculate what is going to be the distance list. And of course, we'll have a separate function for that. So in this case, we are going to be using the self dot dist metric over here, which is basically going to be the Euclidean distance. So here we'll basically pass the x, and we'll also pass the self dot x train. So the entire distance list that we are going to be having, like the pre-trained set of classes. And here we'll define our y sorted. So this is basically the sorted list of values that we'll get from our data, which will be essentially equal to y. And here again, what we're going to be using is, and here we are basically going to be running a loop. So y for, and then we'll define y in sorted, right? So we are basically going to be passing a zip of the values. So we'll just pass the distances and self y train over here. And then after this, what we'll basically do is that we'll continuously append this over here to the list of distances. And finally, what we'll do is that we'll basically return the list. So here, what we'll do is that we'll return a list, and this will be the list of mapping the values of, so basically the end result is that when you are calculating Euclidean distance, you are then sorting them into this ascending order. Then you pick the value of k, which results in the k shortest distances. Now we're basically mapping that, okay, for each of these distant points, which class does it actually belong to, right? So you're basically returning that. Returning the list of them using the map function, we're basically returning the value, which is the most common over here. And we're also passing our neighbors, which we have defined. So this will help us to return this particular value. Now, of course, one thing to keep in mind over here is that we'll also have to, define these particular values. So we need to define what our most common and the Euclidean distance are going to be. So in this case, we will go ahead and define a couple of functions that we'll just define above this. So let's go ahead and define it. So we'll first define the most common function as well, right? So in this case, what the most common function basically expects is to have a list. And in this list, what we're doing is that we'll basically just return the max from the set of list, right? And where basically the key is going to be is actually equal to list.count, right? So this will allow us to calculate it. So we'll pass this particular list, and we'll also just define a separate function for calculating the Euclidean distance. So Euclidean, and here again, we will have the point that we wish to classify alongside our data. And using this, we will just simply do return np dot square root, right? And here we are basically passing the np dot sum of the point minus data and x is equal to 1. So this will help us to calculate the Euclidean distance. So we can run this and let's just see what is this error. It's not closed. So I can again. So this is the Euclidean distance, and now we have basically defined our distance metric as Euclidean, where we are calculating the distance metric, and so hopefully this is the way that basically returns. Now, once we have gone ahead, so these are basically the helper functions for the most common, which will represent an intuitive way of finding the most common element inside of a list. And then, of course, we calculate the Euclidean distance. So once we actually created this KNN class, where we'll specify the K and the distance metric, to implement this, we have used a fit method that is similarly used, is actually widely used inside of scikit-learn as well. So we are going to be using this. Now, finally, what we'll also do is that we'll also have an evaluate method over here defined for us. So we'll have evaluate. And what basically this will do is that it will evaluate the performance of our model. And we'll basically send in a dataset of attributes and their classes, which will be passed as, let's say, an X test and Y test. And the predictions of the model are compared to the actual classes that we have, right? So we'll have self, and we'll pass in X test and Y test, right? And then we'll compare the values. So first we'll calculate the actual predicted value. So what is the predicted value that we get? So in this case, that will be the self predict with our X test. So we'll use self pred function, which we have defined over here, right? So we'll just use the self predict, or sorry, self dot predict. So we'll use the self dot predict, the X test. And what we are doing in the end is now we will also then define a separate variable known as accuracy, which basically compares between the predicted values and the actual values, where the accuracy is equal to the sum of the y pred, where how many values of the predicted values actually match with that of the actual values that you have, right? Because you're using the y test, which is the testing data that you have, and the predicted values which are coming from y pred. So you just compare that and you run it over the length of y tests, and you can simply just go ahead and return the accuracy. So this returns what is the accuracy given a value of k for which you're defining, because this accuracy allows you to then choose different values of k and see where is the accuracy that is the highest. So you can also have another loop that runs from the values of k from 1 to 20, calculate where you get the highest accuracy, and in a usual condition or in a usual state, that is the most optimized value of k that you should pick for a given dataset, because this will vary from dataset to dataset, right? Of course, every dataset will be a bit different, but this will basically vary from dataset to dataset. So now you can always deploy this algorithm for actually doing the model classification. So for, of course, like for completeness, you can go ahead and optimize the value of k. And we can also now understand that what would be. So like, let's just go ahead and actually run, all of this with an example. So we'll run this class definition as well. And now let's actually, let's say that we have accuracies as one, list. So this will be an empty list. And now we run a loop where we say that, or the case range is going to be between 1 to 30. And now what we'll do is we'll say for k in ks, right? We will simply just say KNN is equal to k neighbors classifier with k, in which we will fit the data with our X train and Y train, right? So we'll pass the X train and the Y train over here, which will basically pass after calling this particular data. So here we are going to be saying k is equal to k. And now what we'll do is that once we use the KNN.fit, what we'll do is that we'll first calculate the accuracies. So we'll first calculate what's the accuracy that we get. So we'll define accuracy is equal to KNN dot, and here again we will use basically the evaluate function, the evaluate method with passing the X test and the Y test, and then we will append it to this accuracies list. So this will return the accuracy for a corresponding value of k. Now what you can do is that once you run this entire loop, you can simply go ahead and plot this. So we can see that we have a figure and we have like an axis. So what is the axis? Where you basically plot it and you define, and for this you'll also have to import the matplotlib. So we'll just import that as well. Import matplotlib as plt. So let's go ahead and run this, all of this together. And of course, I think since you have not defined X train, you can also define the actual values of X train and Y train. So you can always go ahead and do that as well, depending on what is the value that you want to set. Because of course, when you are passing on the value, you're also passing the actual training data, right? So you also have to end up defining what your training data would look like. And for that, we will now define that with the help of an actual data set, because we are basically going to be using this as part of our dataset. In this case, let's take an example of the iris dataset. So if you're not already aware, iris flower dataset is actually one of the most famous datasets that is out there. Now, the goal of this particular dataset is to identify that you have been given these three different categories of flowers, which is the iris setosa, iris versicolor, and iris virginica. And the dataset, if you look at what the dataset contains, basically it contains the list of 150 samples, 50 of each and every different kind of flower. And for each of these particular flowers, you are given 4 different distinct values, which is basically the physical characteristics of these flowers, which are the sepal length, sepal width, and the petal length and the petal width. So these are the physical characteristics of these particular flowers. And every flower basically has a sepal and a petal. So petal is the colored part of the flower, and the sepal is the green part of the flower. Right. So I've been given this data for all of these particular different type of flowers, and we have been given over here, as you can see, that their length and width in centimeter, and then which particular species does that particular data actually belong to. So does it belong to iris setosa? Does it belong to iris versicolor or iris virginica? So I've been given 50 dataset points for this, and this is one of the most common and really good datasets to at least get started when you're trying to basically create a KNN algorithm or any machine learning algorithm for the first time. This is one of the most simplest datasets that you can actually start off with. We'll basically use this particular dataset. So what we'll do is that, in fact, like the sklearn library, right? It actually has the, and over here, like we'll specifically talk about from sklearn dot datasets. So here we are basically going to be using the sklearn dot datasets we'll use the import load iris function, which will allow us to import the data set, right? And if you just look at the data set over here, if I print it out, so you can see that it prints the array over here, which is the first array which contains the data, which has all of the values, right, in centimeter, starting off with sepal length, sepal width, petal length, and petal width. As we go down, you'll also find the target, which are basically 0, 1, and 2. So the 0 and 1 and 2, what they denote are essentially, and you can see this over here in the code as well, right? So here is like code where you load the iris dataset, you get the data function, and then you see that the target actually is the 0, 1, and 2. So this is the one hot encoding where you're representing your data as numerical values. So 0 is representing the dataset that's there in iris sedosa, 1 is representing iris versicolor, and 2 is representing iris virginica. So you have these three different data types and data sets, and all of them are being represented as either 0, 1, or 2. So that is the end data that you get. You also see the target names and a bunch of other data, right? So when I implement this actually in Python, as I've done it over here, where we have imported the actual data set and given it the name of iris, we get a lot of metadata. We get the target names, we get some description, some characteristics that we have a total of 50 of each of the three different classes. We have four numerical categories, right? The lengths of the data sets and the names. So there's some information about the data that can be useful. So now what we're going to be doing is that we have imported our actual data set itself. Now let's go ahead and define, of course, now remove the target data to be the y coordinate. So x would basically just be iris dot data, and y would be iris dot target. And we will also just pre-process this data. So we'll use basically the pre-processing. So we'll import from sklearn dot pre-processing. We'll import standard scalar, and we'll now just pre-process this data. Let's go ahead and do that. Scalar equal to standard scalar, and then x equal to basically dot fit transform, and we'll pass our x over here. And now what we can do is we can go ahead and split our data. So in this case, we are going to be passing it through the train test split function. So for that, we'll also just have to import this over here. So from sklearn dot model selection, import train test split. So now we have over here, we have basically gone ahead and split our data into the training, testing, and training data and the testing data. So all of this has been done. So now if we actually run this over here, right, this should work because now we have defined our xtrain and our xtest. And as you can see that in the case when the value, as you can see over here, right, that this particular diagram, as we have now drawn it out, this kind of gives you a good story of what is the KNN accuracy versus the value of K, where basically looks like our, K or, the KNN model will basically work great when there is a low value of K, because you can see that the highest amount of accuracy is when you are like, let's say, taking a value of K as 3. It increases again when you have the value of K as 5. And then you can see like certain dips when you increase the value of K. So this should give you an idea that lower values of K are generally preferred over larger values of K. Like I think mostly any value of K between 3 to 5, 3 to 10 should be a good value of K that you can select. So this you can run across every type of data that you actually work with. So what we have basically done is that we have implemented a simple and an intuitive K nearest neighbors algorithm with under 100 lines of Python code, which is basically calculating and of course, we did this for this, KNN algorithm for this load iris dataset. Now, instead of implementing the K neighbors classifier functionality yourself, you could actually also just have this much amount of small data and implement this with the help of the sklearn library. So in this case, the other alternative approach to solve this is you have all of this. So you also do from sklearn.neighbors, you'll use the K neighbors classifier. And then once you have basically trained your data, you can define the KNN as clay limits classifier. You can define what is the K value that you want to select. In the scikit-learn, we have the denotion of K as n neighbors. Then you fit the data, and then what you do is that you can do y pred as being equal to KNN dot predict, and you pass the X test, and then you can say print the value of y pred, and also print the value of y test to see like how did the actual algorithm perform. So this is the predicted values, this is the actual values. And you can see that I think most of the values are similar, right? So to a high degree, I think only this value did not match. This value did not match the third value, and most of the other values are actually matching. So we can confidently say that the algorithm is actually performing fairly well with the value of k selected as 5. Of course, like if you change the value of k to something larger, it might result in a lower accuracy of the model, right? So this is a quick summary of what we have kind of covered with the KNN algorithm. Again, the study material for the KNN algorithm will be accessible to all of you after the end of today's session. But if there are any other questions by anyone, feel free to ask. Otherwise, I think we have kind of come to the conclusion of today's session. If there is any question that you might have, feel free to ask your questions. Now, the other thing that you can actually also always do is that when you actually have the KNN classification, you can also actually have the certain number of samples, because basically the number of samples and the number of features that you have, the weights that you define, all of those actually also do come into the picture. But we'll perhaps talk about that sometime else. Perhaps when we go deeper into the neural networks, then we'll understand how weights play a really important role inside of neural networks. Because the idea really is that making the prediction, the first thing that you do is you calculate the distances, then you return the indices of the first k neighbors, then you extract the labels of those particular indices, and then you calculate like what's the most common label that you're finding. And that's what we have done with this particular example. So if there is any other question, feel free to ask. Otherwise, I think we can uh, probably conclude the session. But yeah, if there is any other question, do let us know. But it doesn't look like that we have any other questions. In the next session, we'll now discover even more projects around KNN, linear regression. We'll also provide some assignments, and we'll have the next set of algorithms like the k-means algorithm, logistic regression. So we'll be moving to some of the more advanced algorithms. So looking forward to meeting all of you in the next week. Thank you.